Hello. Hello, everybody. You made it. Excellent. Second day of Voxxed Microservice. First presentation is the worst. So, welcome to our presentation. Today we will talk about reactive design patterns for microservice on multicore. Lot of buzzwords we are seeing here. It's good because we have a lot of people in this audience. So, who are we? Who is ThreadZone? We are a team that works in high-performance software for mission-critical applications. So we've been working 3 years on a very complex application, which is trading software for exchange. And today we're presenting our experience, how we designed this software, and how we made it work at good performance. So today I will be talking, me and Alain will giving this talk. So the outline of the presentation, 3 parts. First part is why multicore impact the performance of microservices. Second part, given by Alain, reactive multicore patterns. So we have 7 patterns we will show in this presentation. And finally, our vision, what's the best roadmap to design modern software. So let's start. This is a typical microservice, a modern microservice application. We have several microservices in the architecture. The microservices communicate with each other using messages, using REST API, HTTP, it depends on your application. And if you want to design the microservice to be asynchronous from bottom up, using reactive manifesto principles, we need to have actor model implemented in each service. So we can have here akka, Scala, or even simplex, as we will show later. So basically, this microservices, we have a lot of messages communicating with each, between the actors and between the services, and we need a runtime to handle this message passing. And when we look at the performance profile of each microservice, it should lie somewhere in this spectrum. So what we are showing here, we're showing the performance profile of an application. It's a combination, it's a ratio of computation and communication between different components of the system. So when we have an application, we have more computation than communication, we are in what we call batch processing. And as we move forward in the spectrum, downwards, sorry, the spectrum. So we go into more communicating part between different actors in the system. And here we are in what we call highly interconnected workflows, or what we know as fast data. So fast data is mainly when we have components communicating at a high frequency, and they are doing small computation in each part. So how does this impact the architecture? So we move from an architecture that is like this. We add more interactions with fast data, and especially we add more interactions, not only more communication, but even we will have unbalanced communication between the actors. We can have some critical paths that are communicating at a very high frequency, and other paths that are communicating at a smaller frequency. And this means that there is more challenges to schedule these actors on multicore, and to be sure that we'll have deterministic performance at the end. And if we add the roadmap of multicore, what we are seeing here is the evolution of multicore architectures from 2 cores 2006 to now 24 cores per CPU socket, Intel architecture. We were seeing at the beginning that each microservice run on one machine, and as we add more cores, we have more microservices that should run on the same machine, same CPU socket. So this actually impacts what we expect as users. We expect to be adapted to Moore's law. So Moore's law is when we add more cores, we will expect to double the performance. And when we double performance, it's actually we should have double performance at the same cost. So we don't want to change the software to double performance. We want to double performance automatically. This is what we expect. But unfortunately, this does not happen always, as we'll see later. So if we have more microservices on multicore architecture, we can have something like this. We have two microservices in this example, where they are we have the possibility to share, to have several actors sharing the same CPU resource, same core. We don't. It's very challenging actually to have a deterministic performance when we have several actors sharing the same core. So if our runtime does not handle these issues, we will have undeterministic behavior of the performance. So when we have more actors sharing the same physical resources, and we expect perfect scalability of our performance, in reality, this is not true. We don't have perfect scalability, and the reason is given by what we call Gunter law. So this is a law that is it's a very elegant mathematical equation that we can model the performance of a system based on queuing theory. And basically, what this law says, there are two parameters that impact the scalability of the performance. The first one is contention, and the second one is coherency. So when we have contention in a system, software and hardware, we have a sublinear performance. We don't scale linearly. We have sublinear performance. And when if we add coherency more than contention, we have a negative scalable performance. So the whole issue is to find what are the sources of contention and coherency in a system in order to solve them. So what I will show next actually are the main two sources of contention and coherency. So the first one, if we take the picture from before, we have actors that want to communicate with each other, as we saw in the microservice diagram. And if we imagine that an actor, let's suppose that an actor actually is equal to one thread, we will have this type of interaction between the actors. So this is spaghetti. And why does this impact performance? Well, actually, as I said, an actor is equal to one thread, this means that it should be scheduled by the OS. So we have context switches from the operating system. So it takes more latency. And if we have if we have a very complex software architecture, we have a lot of actors here, this will be really to deteriorate the performance of the system. So what we want actually is we want to move from a communication model like this to this. We want to mutualize the communication between cores. It should be at the core level. And if we have inter-core communication, we have a second notion, what we call coherency, cache coherency. I don't know if you guys are familiar with this with this image. This is a typical multi-core architecture that actually your microservices are running on it. And what I'm showing here actually is how is the cache hierarchy of the multi-core. So we have what we call the private cache of each core, and we have a shared cache. It's normally the L3 cache or last level cache. So the private cache is what gives us the most deterministic performance because we don't have contention on this memory. So if there is we have a core that wants to access the data, it will access in its registers at the same CPU cycle. Let's imagine, let's say it's 3 gigahertz, so it's 0.3 nanosecond. So it's the same cycle we will access the registers. If the data is not here, we'll go to the L1 cache. It will take around 4 cycles. If we have a cache miss, we go to L2 cache. It will take around 12 cycles. And then if the data is not in the private cache, then we go to what we call the turbulence zone or the shared memory. And it takes at least 30 cycles to access data. So if you want, we have two synchronization between two threads. The way it's done in practice, data that is that want to be read by core, let's say N here, it should be copied to using cache coherency mechanism to the L3 cache, then put in the L1 cache of the other cores. So this mechanism, it's done in an automatic way in the hardware. It's called the MESI protocol, and it takes at least 200 nanoseconds, 600 cycles. So one sync is 600 cycles. And to make things more fun, we add business requirements. So in capital market industry, we are asking for more volumes, million message per second. We need at a higher speed. So we're talking in microsecond levels. And of course, to add more fun on this equation, we want the application to be stable, deterministic. So we expect performance determinism at 90% yield, 99% yield, even more 99.99% yield. So the way we solved it in ThreadZone, we did not find in the literature a framework or runtimes that helps us achieve these performance requirements. So we designed our own, and the principles of our framework are very simple, and they will remove a lot of complexity development complexity, as you see later in the patterns. So the first principle is, if multi-threading is a problem, well, let's do one thread per core. It's one thread per core. After all, multi-threading is a solution that was invented for multitasking on a single core. It was never invented for multi-core architecture. So we used it because we have already had this operating system that implements multi-threading, but it's not the best one for if you want good performance. So the first principle, one thread per core, so we eliminate context switching. The second principle, we want to increase the core utilization, so we share multiple actors per core. And the third one, but to schedule these actors, we have an event loop that is running infinitely. This event loop will check the events received from other cores or the same core. It depends if the actors are communicating on the same core. And then it schedules the right callback for the right function for each actor. And the way simplex is, so an event loop, if it's idle mode, it's around 300 nanoseconds. If it depends on the machine, so it can be 200, can be 400, depends on the frequency of your machine. And the event loops actually communicate with each other in a unidirectional communication channel. So what this means that if we have multiple actors that want to communicate with other actors on another core, we mutualize the synchronization. So we have one synchronization that is done instead of multiple synchronizations. So and the communication is done in a log-free mode. So simplex is, as I said, is a runtime that is that sits on top of any operating system to develop actor model and microservices that run efficiently on a multi-core CPU. So we handle the multi-threading, the cache memory, and we provide a very simple API, as you can see after the presentation in our demonstration, in our booth. And of course, when we talk asynchronous systems, it's if we have a solution, efficient solution without the right tools, it's very difficult to develop, debug, and even deploy. So we have developed studios like debugger, tracer, rich list of connectors, and we have also parts for, so we have part components for the dev and component for the ops. So we have profilers, we have real-time monitorings, and we have also, we can integrate with Docker and Kubernetes. And once we develop the software with Simplex, we can run it, deploy it on any multi-core architecture. We just have to choose the right Simplex. So we can run it on embedded server and cloud. So this is a small joke. And, now the next section we'll talk about what are the best practices, what are the efficient design patterns to run on Simplex. We have two very good references. I have them on my desk. I have read them all. They are great to design actor models, but they are not, there are no patterns that target the multi-core architecture. So what we explain later are patterns for multi-core optimization. And now I will make a small test challenge in order to be sure that you are all wake up. So we have 3 million microseconds to find Charlie, not me, Charlie here, or Waldo or Wally, depends on where you come from. 1 million. 2 million, 3 million. Thank you. So we'll have the answer at the end. Did anybody find it? Oh, you were the closest. That's why. So the idea of this image actually to show you that patterns, there are no right or wrong patterns. We have some patterns for Charlie here, Waldo, that is full in the image, but to find the right exact pattern, it's very hard, and we need to dig in the details of the software architecture. And next, I will give the second part to Alain.
Thank you. So, thank you, Charlie. I will talk now about some patterns you can apply on multi-core architectures. You are used to patterns on microservices on different servers. When you understand that your services are running also on multi-cores and they interact between themselves inside one multi-core CPU, you understand also that you need to apply other patterns. However, most of them looks like the network pattern you already know. But let's see that. So first thing is messaging. When you have microservices communicating, usually you use networks, REST. However, if you really need to optimize your communications, you need to think about how they are deployed. So if they are on several servers, okay, they connect with network. If they are on several CPUs, they will use QPI. If they are on two separate cores, they will use cache coherency. And when you push a message, an event from an actor to another actor, it should be seamless for the developer. So that's the first point. When you push something, you don't need to know where it goes. However, whatever running your services, it should use the correct interface. It's not enough because, of course, when two services are on two separate cores, okay, you use cache coherency. But what if they are on the same core? Usually you don't think about that. But if they are on the same core, you still can do some optimizations. So you can still push a message, and so you will use an event loop. So it will take about 300 nanoseconds. However, you can also do a direct call. Why? Because we have started saying that we should be mono-threaded per core, and all actors on the same core share the same thread. So you can have great optimizations just like that, because services know that they are running on the same core. Of course, don't do that every time, because if you do only direct calls, you will have many issues. But sometimes you know that you should do that, and you will have lots of better performance. So let's talk about another pattern. Simple one, again. I'll always talk about simple patterns because we need to start by that. So here, in this example, I have one producer sending data to 3 consumers, but these consumers consumes exactly the same data. The question is, if these actors run again on the same core, not the consumer ones, what can we do? If you were on if it was not cores but servers, you would try to mutualize the communication, because communication has a cost. It has a cost when it's network, but it has also a cost, like said Charlie, when you are making communication between cores. So you would like to mutualize that and try to add kind of a proxy to take the data and distribute the data inside the core. So it seems that you have a contention point, but actually it's not, because you replace synchronization between cores with here direct calls. So you could say, are you sure that it improves something? So yes, you have improvement. So depending on if the cores are on the same socket or on two different sockets, I mean the same CPU or not the same CPU inside the same server, you will have great improvement in terms of communications. So this is something that is really important to think about when you are designing your microservices running on the same server. So saying that you have one thread per core and lots of cores and you have many services, the question is how to monitor everything. So here is a simple example. Let's start by having several actors. These actors here are running on several cores, and you need to calculate the throughput, the global throughput, and also the local throughput per core. So if you had one thread per core, not per core, one thread per actor, it would be much difficult to get the real throughput, because to get a global throughput, you need to do synchronizations, and you would like to avoid that. So here, with this course, because I have one thread per core, I can have, here a monitor actor, but because it shares the same thread, they can share a variable and say, okay, I received a message, +1. I receive another message, +1. I do that per core. And I know that when I change the variable and I increase it, my counter, no one is changing this counter. So I don't impact my performance just doing simple local monitoring per core. Then, once done, once per second, for example, I can push a message to a remote service to say, okay, this is my throughput on this core and on this core, and I do the final calculation at the end. But my critical path has not been impacted. And if you want to see an example of that, a working thing showing that we can do really precise performance monitoring without impacting the performance, we have a demonstration over there. Okay, so this is one kind of monitoring. Now, another kind of monitoring is to understand what's happening on the CPU. So it's not, if you monitor the CPU and you see that it's a 100% use, it does not mean that you cannot work more. I mean that if you do a network read and write, often you have a while true thing, okay? And okay, your CPU is used at 100%. However, you still can read and read more messages. So it's not a useful figure. So you should try to find how to know the real percentage of use of your CPU and know when you need to stop to send something. So this is a simple example of a loop working, so the event loop. And every loop here is idle. So I do nothing, like a while true when I do some networking thing. Then, after that, I have some loop working, meaning that I have received an event. So my actor is working. So in that case, when it works, here this loop lates more. So it's not perhaps not 300 nanoseconds, but 1 microseconds. I don't know. So the only thing you need to do is to know the time, the cumulative time of each loop and do the ratio with the total time for the calculation. Doing that, you can be really precise and know that, for example, you are using 82% of the core right now. So you are in danger, and you should do, I don't know, some throttling, prevent someone that there is an issue, do something. But you can do that. Again, I don't think we will have time to show you that here, but over there I can show you something. This could be the demonstration, but let's see later. So here is another example of monitoring. So we saw how to monitor cores. We saw how to monitor actors locally inside a core. Another question often is, okay, I'm pushing a lot of data, and my destination cannot process the data I sent. How to know that? So what I will explain here is how we do that in the simplex part. So how the communications are done between two actors. Actually, it's pretty simple. So we have two event loops there, and we have something called a batch ID. And the batch ID change only when this core has taken the token, okay? And if it's done, the batch ID changed. If it has not been changed, I know synchronously that it's not time to send anything, because the last batch has not been read. This is what you would see in such example. I mean, in the example on the left, you see that I sent prices, actually lots of prices, but because here, oops, you see 71 and 71, it means I have sent, received only 71 messages. However, it's only 71 because a lot of message has been queued. When you tried the batch ID thing I have discussed just before, you understand that actually you could drop more than millions of messages, perhaps drop or merge or anything. So such thing is important to implement in any framework for dedicated to performance. So this is a typical example of fix engine. I don't know if you know fix here. So in the capital market industry, usually and often you discuss, so the communication is done with the fix protocol. The fix protocol is something very heavy, but easy to use. So in the example of a stock exchange, they receive fixed orders. An order is a buy or a sell order. So this circle actually is a big new order. But the fixed protocol imposes something. It says that when you send a new order, you should receive an acknowledgement from the stock exchange. And in this acknowledgement, you need to give everything I give to you in the new order. So somewhere, the stock exchange should store this, even if it's, there is a lot of data. So what could be a pattern for trying to avoid or to optimize the performance? So again, the issue with performance is the fact that you have a lot of cache coherency, and so meaning communication between cores. You need to avoid that, and you need to avoid to use a lot of cache inside your core because you want to avoid cache misses. So here is this example. As a stock exchange, I need to store all orders of my clients. So if I had to store every fixed orders, it would cost a lot, and I would decrease a lot in terms of performance. So what should I do? The big order I have, I split it when I receive it. And actually, I keep inside the first core the big part I don't want to store inside the very critical component of the stock exchange. So I store one part, and I send only the useful part. Then, in the acknowledgement, I give back only what has changed, and then I send back the big order. So doing that, which seems simple, actually at the stock exchange site, I can store much more order in the cache level 2 Charlie was talking about. Because just before that, I had to store 200 bytes per order. But now, because I have split it, I can store 32 bytes only per order. So it means that I could, in a typical CPU, store 8,000 orders per core, which is much better than before. So here is another example of, let's say, routing pattern, actor directory. When an actor receives a message, it needs to know where to send the next one and to know the ID of the next actor. So how to know this ID? What's the address? This is how to know that, how to say that. The address could be huge. I mean, so the address of an actor, you need to know in which core, in which server. Perhaps you have some optimizations. So the address of the actor could be 8 bytes, 10 bytes, 15 bytes. So it's not a very short ID. So in this example, the green actor have received a message, and you have a table like anyone for about your directory, and in this table you have, for example, the incoming key of your client. For an exchange, it would be an ISIN code, okay, a 12 bytes key, and you have the ID of the destination. And this can take about 1 megabyte for a list of 50,000 actors, because, okay, it's only a multiplication. So when Charlie talked about the core design and caches, a cache is about 256 bytes, and so I'm really higher than that. So I increase a lot my cache misses inside my core doing such table. So I would like to avoid that and try to reduce my map, actually. So how to reduce it? We should understand that we have cores, and we should use the fact that we have n cores and not just 50,000 actors. So let's do something else. You have here the incoming key, but in this table, I don't put now the ID of the actor ID, but I put the core ID. something that is very short and could be only, for example, 1 byte. And I have a second table. And in this table, I put the ID of a local router, like before, and an index of the actor to let the router find the actor. So if I do that, I have splitted the map into 2 maps here and some other there, but they are much smaller. So now, for doing exactly the same thing, the memory size is 0.65 megabytes. So it's we save about 50 or 40% memory cache doing just this pattern. So you will save cache misses, so you don't do on the L3. So you will save performance just because of this simple pattern. Je vous montre une démo. OK. This is for you.
Okay. So, having said this, very simple patterns, as Alan said, but when we design complex software, it's a combination and the aggregation of these small and simple patterns that can lead to either we have good performance or very bad performance. So if we don't use them well, we have very bad performance. If we use them well, we have very good performance. So this saying from Henry Petrowski, he's blaming the software guys that they are not keeping pace with the hardware industry. I understand him very well because I used to come from the hardware industry before, and every time I say, why these software guys are not, we're giving them multi-core, higher frequency, more cache, and why they're not doing the job. And now when I move to the software industry, I understand that it's actually very complex. So the software layer, the software frameworks that exist, that we use them, are very complex. We use a lot of them. Most of them, when we are designing application, we don't have control on the hardware, and we don't actually know how things are running on the hardware. We have a lot of virtualization, a lot of abstractions, and so how we solve this? We don't want to develop in assembly, right? We cannot design complex software with assembly language. It's impossible. So the roadmap to move from spaghetti code, multi-core spaghetti code, to a multi-core ravioli code is actually to choose the best thing that we as humans we can do it collectively. Complex software is not done by one person, done by all of us. So how we do it? At the design level, so architects, we want to design directly in a concurrent way. We want to think concurrently. So the actor model and microservices are an answer, a good answer to already express the requirements of the system and the architecture of system in a concurrent way. But we design it concurrently, but at the end we want to develop it. So we have a team of developers that want to develop these concurrent blocks. But we as humans, our brain is very good to develop in a sequential way, not parallel or multi-threaded. It's very hard to develop a multi-thread application that is bigger than 7 threads. This is completely neuroscience. It's called Miller law. 7 threads, we cannot do better. So we want to develop monothreaded. So what we provide in Simplex is actually a monothreaded development for a concurrent design. And then we want to run it parallel. We run it parallel, actually if we design concurrently and it runs on a single core, it's not parallel execution. We want to run it on a parallel cores. And we want to execute reactive. So by reactive, our application should be responsive. It should be resilient. It should be deterministic also in performance. So to execute reactive, we want to be sure that the under layers technology that is used allows us to execute reactively a complex software. And we think that with Simplex, we bridge the gap between complex software design and efficient execution on multi-core architecture. So the core technology is now open source, starting from end of May. You can go to our booth. We show you. I have a lot of demonstration, code demonstration, performance demonstration. So please come to us. Let's talk. And I will let you take photos. I still have 4 minutes.
We can show a part of the demonstration actually.
Yeah, and for the people who did not find Charlie or Waldo, he's here. Thank you. Any questions?
So should we show you a demonstration over there or here? We have 4 minutes. Here? So for those who... Tu peux juste le prendre.
C'est ça. Mais je pense pas...
Je vais faire juste rapide. Tu vois quelque chose?
Ouais.
T'as plus de souris, ok. Ok, so actually...
Tu dois l'exécuter.
Ouais. This is not the code demonstration. The code demonstration will be done over there. However, what we show here... Okay. Let me show you something. So this is one core, another core, another core, another core, okay? And I have producers and 2 consumers there. What you see here is the throughput. What you see there is the latency between the producer and the consumer. What you see there is the distribution. Why I show you that? Because we talked about monitoring in real time. What you see here is it's less than 1 microsecond, or about 1 microsecond. It means that we can monitor in real time without changing or impacting the performance. This is the demonstration of that. Just because the latency is low. I don't care about it's low, but it means that monitoring is working. And here it's the same. The pattern about how to know the charge of the CPU, the useful charge of the CPU, it's exactly that. You see that we use 60% of here's the CPU, and we can increase the throughput. So this demonstration is just to show that it is possible to do what we are saying. So you can have best performance and you can monitor everything. What you see there, why you have this like that? You have this because it is the cache coherency protocol. This is here exactly the communication time between this course and this one. That's what we see there. And actually, let's do something else. Okay. And this time, we put exactly the same actors or services on the same core. And on the same core, of course, we cannot reach the same throughput. However, now this is a latency. And still, we can monitor it in real time. So you see exactly the difference between communication between cores and no communication between cores. It seems very low latency and not useful for you, but actually when you start to add these communications and bad patterns and you made them interact, it's not nanoseconds that you will see. When you will reach 100% of the CPU, you will have milliseconds, seconds, and perhaps just crash your applications. And sometimes it happens and you just don't know why. But usually it's because of such things, such patterns not applied. That's all what I wanted to show you. We wanted to show you. Thank you, guys.